Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it: planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, NASA's chief scientist, and this is Gravity Assist. With me today is Jon Jenkins, and he's the co-investigator for data processing on two absolutely fabulous missions, Kepler and TESS. So Jon, tell us what that means. What do you really do as the co-investigator for data processing?
Well, Jim, what I do primarily is to design, develop, implement, and then operate the science pipelines for both the Kepler mission and now for the TESS mission. And by science pipeline, I mean the facility and the software that allows us to take the raw measurements coming down from the spacecraft, the image data, and we process it to turn it into planet candidates, essentially.
So you're sort of like the first line of defense that sees some of these exciting things that come back from the spacecraft.
Absolutely.
So what are some of the things that have really popped out in the data that you go, ooh, that's neat, or ooh, here's something that could be exciting to analyze?
Well, certainly with Kepler, I think some of the most exciting signatures that we saw in the data were ones that we didn't expect to see. So, for example, when we collected the first science data from Kepler and brought it down, that was our first opportunity, essentially 10 years ago, to see whether or not Kepler would actually work, because it was a very challenging experiment and nobody had done this before.
So what's the basic principle behind how Kepler works?
Well, Kepler works by observing a field of stars and measuring the brightness of the stars over time, looking for instances when a planet crosses in front of the face of the star from our point of view. And when that happens, the star winks at us, and that repeats. So we see a dimming of the starlight once every orbital period of the planet. And the depth or the amount of light that drops tells us what the size of the planet is relative to its star. And the interval between what we call transits or crossings of the star by the planet tell us what the year is for that planet, the orbital period of that planet.
You know, so Kepler's been really successful because it's looked at so many stars all at once in its original part of its mission. How many stars did it look at simultaneously, and how fast did it look at each star?
Well, we could observe as many as 170,000 stars at any given time. But typically the largest number of stars that we observed at any given time was 165,000 stars.
Wow.
Now, we measured the brightness of each of those stars every half hour. But we had a small sample, 512 stars, for which we could make measurements every 1 minute. And that actually is very important because we need to know about the stars in order to know about the planets. I said before that we could tell what the size of the planet is by looking at what the fractional drop in brightness is when a planet crosses a star. But that's a relative measurement. So we need to know how big the star is in order to infer with precision what the size of the planet is. And so for the brightest stars that were at least 12th magnitude or brighter, we could monitor the stars at 1 minute and actually measure acoustic oscillations or pulsations of the star caused by starquakes. And this is phenomenal.
Yeah, so it's not just transits, it's not just planets. Well, even sunspots. You know, when our sun has some enormous sunspots in its cycle,
that's right.
Its overall light in certain frequency ranges, like the Kepler frequency range that it observes, can be dimmed just from the sunspot.
That's right. In fact, if we could see another Earth-sized planet transit the sun and just measure the brightness, you would see that the drop in brightness from a typical star spot would be as much as 5 times deeper.
Wow.
Than the drop in brightness due to an Earth-sized planet crossing the face of the sun.
So this is really a new and important dimension for other scientists that are using Kepler data to be able to cull through that and look at how active many of these stars are.
Oh, absolutely.
In fact, my understanding is, you know, our star, you know, we call it a typical star in the galaxy.
Right.
You know, it's classified as a G2 star. There's something like 10,000 G2 stars that Kepler looked at, you know, in its prime mission. what kind of information you can get from that is the sunspots and their activity, and really kind of understand how active G2 stars can be. And that's true for almost any star.
That's correct. And so one of the unsung stories of Kepler is the fact that we were able to conduct astroseismological investigations of these stars. That's the study of the songs that the stars sing as they ring like bells. And like bells, the more massive and bigger the star is, the lower the tone. Stars like the sun ring with a typical periodicity of about 5 minutes. So that's why we needed the 1-minute samples. But by studying the tones the stars are ringing at, you can measure the size and the mass of a star to a couple percent. And that's phenomenal because we can't see the star. We can't resolve the size of the star by looking at the images. We're just seeing point sources. So it's phenomenal that from hundreds or thousands of light years away, we can actually measure the mass and the size to a couple percent. I don't know about you, Jim. I don't know what my mass is to 2%.
Yeah, okay, that's really phenomenal. So let's listen to what a star song could be like. So, when Kepler looks out and sees this large a population of stars, I can just imagine that it's looking at almost every type of star from what we classify as A all the way to M and others. Is that true?
That is true. For Kepler, we had target stars that we observed, and over the lifetime of the mission, we observed over 200,000 stars during the Kepler mission itself, ranging from late A stars all the way down to early M stars for the most part.
Yeah, where the A's are the really big stars and
That's
the M's
right.
are the much smaller stars.
That's correct.
Now, you've done a lot of work yourself and doing the science analysis. What is some of the fantastic things that get you excited about looking for planets?
Well, I think one of the most exciting things that came out of Kepler in terms of exoplanets that we didn't expect was the fact that we observed well over 400 multiple transiting planet systems. These are cases where you don't just see one planet crossing the face of its star periodically. You see multiple planets. You might see 2, 3, as many as 8 planets transiting a star. Now, Kepler only observed for 4 years. And so that means that all of these systems are very compact. The orbital periods are much smaller in general than the orbital periods of the planets in our solar system because we weren't observing long enough to see the Jupiters in 11-year period orbits. In fact, Kepler 11 was the first really good example of this kind of system where you had 6 planets orbiting, and the inner 5 were within the orbit of Mercury, while the outer one was between the orbit of Venus and Earth. So these are small, compact planetary systems compared to our own. And that means that nature really likes to make such planetary systems because we saw so many of them. And that means that our general picture for how planetary systems form as a consequence of the collapse of a protoplanetary disk, the inner portion of which collapses to form the star, and the outer part of this disk aggregates into planets.
When I was going to the University of Iowa and I was getting an undergraduate degree in astronomy, we all recognized as scientists, oh, sure, there's probably planets out there, but we'll never be able to see them. The stars are so far away. So it's phenomenal to think that in our lifetime, that some of these techniques have come out that really demonstrate that planets are everywhere in our galaxy. Now, Kepler observed a particular area for, as you said, several years, up to about 4 years, and then in its extended mission, it changed that approach. What happened?
Well, the worst thing happened to Kepler, and that is that we lost the second of our 4 reaction wheels. Now, we use reaction wheels. They're kind of like gyroscopes to control the pointing of the spacecraft. It's a very efficient manner to do so, but you need at least 3 healthy operating reaction wheels to do that. And in May of 2013, the second one failed. That meant the end of the Kepler mission as we know it, because we could no longer point our spacecraft at the Kepler field of view. But a clever engineer at Ball Doug Weimer, came up with this idea of how we could operate with two wheels using the solar pressure, so the photons bouncing off the spacecraft,
Wow.
to balance the spacecraft so that we could control the roll angle. So with the two reaction wheels we had left, we could control where we pointed on the sky, but we couldn't control the roll angle. And we needed to control that. So we developed and initiated the mission called the K2 mission, which is the follow-on mission to Kepler, using the Kepler spacecraft, where we're able to observe a field of view in the ecliptic plane, so in the orbit plane of the planets around our own sun. We can point at one of those fields for up to 85 days or so. And that's been a phenomenally successful mission, allowing us to greatly broaden the science reach and impact of the Kepler spacecraft.
You know, one of the things that came out this last year was a star, TRAPPIST-1, that was close to our sun, 39 light years away. Okay, just right around the corner, right? And it had 7, planets, and these are big bodies. You know, these are all Earth-sized, and Kepler's had an opportunity to observe this system too.
That's correct.
What's another fantastic discovery that Kepler's made, John, from your perspective?
One of the most fascinating discoveries that Kepler has made is that planets don't form just around single stars, but they form around binary star systems.
Tatooine.
That's right, exactly like Star Wars, which I remember in 1976, my dad taking me to see Star Wars, and seeing Tatooine and seeing the 2 stars, setting behind that planet. And indeed, part of what brought me to the mission was that I was part of a very small team of scientists who were trying to find planets orbiting CM Draconis, which is a small M-class pair of stars. And we believe that if there were stars transiting this system, that an Earth-like place, a habitable zone, would be in a 17-day period orbit. And because it's so small, we could actually, from the ground, determine whether or not there were planets as small as Earth there.
By spending a lot of telescope time, but staring at it.
We observed for 6 years. We placed really strong upper limits on the presence of any planets in that system, but we never discovered any.
Okay.
And it took Kepler to fly before we found the first circumbinary planetary system, Kepler 16b. And since then, we found a handful of other such systems. And what's interesting is that within the first several discoveries, we discovered a planet in the habitable zone of a circumbinary planetary system.
Wow. This is one of those kind of discoveries that the planetary scientists even are going to be stumped for a while.
Right.
We have to really figure out what this planet is like. If you look at a star, chances are it's got a planet, at least one. And so many have, as you've already talked about, quite a solar system, more so than our own. But what are the kinds of sizes we're seeing, and what's that kind of distribution?
Well, in terms of the planets that we've discovered, we discover more smaller planets than we do larger planets. And that's very interesting because it's actually harder to find the smaller planets. It's kind of like if you were blind and reaching down into a pond fishing, you really want to find the small, cool fish that are down there at the bottom. But the warmer fish, because the water is warmer at the top, the larger, warmer fish are easier for you to find because they're closer to you. They're easier for you to reach, and they're easier to find and catch. The smaller fish are harder. They dart out of your hands. And that's the way it seems to happen and what it feels like when you're looking for very small planets like the Earth in data from Kepler. As exquisite as the data are from Kepler, it's still very difficult for us to find Earth-sized planets in Earth-sized orbits. We have only a few examples of planets like that. And in fact, Kepler's main mission was to determine the frequency and distribution of Earth-sized planets in Earth-like orbits of sun-like stars. Mm-hmm. And we're not quite, we have an answer to that question, but it's not very precise. So the most current paper we have and information on that is that about 10% of solar-like stars have a planet about the size of the Earth in a 1-year period orbit. But the error bars on that are very large. So there could be as few as, the frequency could be as few as 1%, or it could be as high as 2, meaning that you have as many as 2 such planets on average. So that's a gap in our knowledge that's large enough for a truck to drive through.
Yeah, but that just means we need to think about more missions to go back up and really close that gap and make that definitive observation.
That's right.
When we look at our own solar system, we have a set of terrestrial planets and gas giants and even in between, our Uranus and Neptune, not as big as Jupiter or Saturn. And you'd think we'd covered the ground in all the types of planets that must be out there. But Kepler gave us a number of surprises. What were they?
Well, one of them is the fact that super-Earth, so planets that are between the size of Earth and Neptune, which is 4 times the size of Earth by radius, are the most common planets we find. And yet we have no examples of these beasts in our own zoo here in orbit around our sun. So we don't know what they could be like, right? I mean, we have no examples in our own backyard. So the question is, are these planets more like super Earths, like large Earths, or are they more like mini Neptunes?
So a terrestrial-based large Earth.
Large rocky.
Yeah, right. Or more like a gas giant, but
that's right.
But more like Neptune.
That's right. So we do have some hints actually coming out of the work that's been done to refine the properties of the stars. As I said earlier, we only know the planets as well as we know the stars. And so it turns out to be very hard when you have a field of view that you're trying to understand what's going on 200,000 stars. It's really difficult to learn as much as you can about each and every one of those. But people are doing follow-up observations to refine the stellar parameters. And so we see that there's a break point now between planets that are 1.6 Earth radii or smaller, 60% or of the bigger than the Earth or smaller, appear to be most likely to be rocky, and planets that are larger than 1.6 Earth radii appear to be more like mini Neptune, small gas or ice giants. So that's a big surprise coming out of the Kepler mission. Again, much like the Maltese, when we were designing this mission, I managed to join this mission back in 1995 while it was still very much on the drawing boards. Our conception of how it would work out and what we had to design this mission to be able to do was predicated entirely on the solar system. So we imagined that every star hosted a planetary system just like our own, and that's what we designed it to be able to do, to find planets like Earth and Venus. And if we were lucky, maybe there'd be some big planets like Jupiter closer in. But it turned out completely different from what we thought 20 years ago.
Well, a lot of people don't realize that Kepler does a lot of fabulous observations, but to really be able to confirm planets versus stellar activities or sunspots or some of the other things that we briefly mentioned, you have follow-up observations. And so what's the network of follow-up that goes on?
So it turns out that most of the planets that Kepler has found are simply too far from us, and the stars are too dim for us to do much follow-up work in order to characterize the planets that we've discovered. So there are a few planets that Kepler has discovered that we can measure the masses directly. Those tend to be the more massive planets, the Neptunes and Jupiters and so forth. But what we can do with follow-up is first characterize the star, the planetary host, much better than we know of beforehand. That allows us to refine the planetary properties. And we're talking about planets the size of Earth. Typically, our understanding of the star might end up changing the imputed size of the planet by tens of percent.
So in other words, there's all kinds of other telescopes that come into play, from ground-based to even space-based, to do follow-up. To be able to lend their support or their abilities to study that system and confirm or even improve on what the observations from Kepler are telling us. One of the other spectacular things, from a planetary scientist, as I sat here and see the fabulous science coming out of the Kepler mission, is that there are planets that are on orbits that they couldn't possibly have been created on. The hot Jupiters and the highly elliptical orbits, as the initial nebula collapses and you end up forming planets, one would think it'd be in a slightly elliptical or nearly circular orbit, but never a highly elliptical orbit. But we're finding those.
We are finding some systems like that. So our best guess as to how this happens is due to late scattering events where you have basically close encounters between large planets. And in many of these instances, a large planet will eject other planets from the system and leave a planetary system behind with highly perturbed orbits compared to the circular orbits that you would expect from the initial formation process.
Yeah, so those gravitational resonances, when those planets fight each other for position, we actually see that in the solar system because Jupiter really carves up the asteroid belt. There are certain resonances that occur for which then Jupiter pulls asteroids out of the asteroid belt, throws them out of the solar system, or actually interior, so that they end up crossing our orbit and becoming what we call near-Earth objects. So this is great connection between astrophysics observations and finding planets and solar system dynamics that planetary scientists do today.
It is. In fact, one of the most recent results out of Kepler has been a study done by Lauren Weiss and her colleagues who've been following up many of the multiple transiting planet systems to look for other planets using radial velocities. But one of the things that she found was that most planetary systems are not like our own solar system. The planetary systems that Kepler has found typically tend to be very regular in the spacing between the planets. And the planets tend to be of about the same size. And in our own solar system, we find that there are much larger distances between the planets and that they tend to be mixed up.
Also when you look at Mercury, Mercury has an orbit and a rotational period that are nearly the same. And so we call that tidally locked. We see one face of the moon all the time, and that's because of our pull and tug on the moon has really evened that out, and its mass distribution is such that we end up with one face pointing to us. So many of the stars that you're finding planets around, actually the smaller stars where the planets are close, may actually be tidally locked.
That's correct. And that could have great implications for the habitability of such planets, because you would expect the sunward-facing side of the planet to be much hotter than the back side of the planet, the dark side of the planet. It's interesting, though, that Earth's closest relative is Venus, and because Venus is rotating so slowly, you might expect it to have a hot side and a cold side, and it doesn't, and that's because it's got a thick atmosphere that permits a subsolar to antisolar circulation of the atmosphere at the top levels, and then it's got a super rotated atmosphere.
If we go back and talk a little bit about TRAPPIST-1, when that was discovered last year, 7 planets orbiting an M dwarf star, smaller star, so it's not as big as the sun, doesn't put out as much light, and so its habitable zone, as we call it, that area where that light on an Earth-sized planet can allow water to exist in 3 phases: liquid, vapor, and even solid. In that system, it turned out all those planets were tidally locked.
Right.
So even though that's a fantastic discovery, it's and we have 3 of those planets in the habitable zone. We have a lot of work to do to prove that they're habitable yet.
We do, and for M stars in general, they tend to be very active and to have a lot of flares. And we know that planets as close as these are to their star, that large flare events could sterilize the surface of such planets.
Yeah, they're really getting hammered. Yeah, indeed.
That's right.
But here's what's really exciting and important about the TRAPPIST-1 discovery, and that is that star is only 39 light years away. That's just right around the block. And it had enough planet-making material that it created 7 planets. So that means when we look around us, our area of the galaxy, of the Milky Way, must have an enormous amount of planetary making material. And so we want to be looking for planets closer to home. And that's where TESS comes in. Can you tell us a little bit about TESS?
Absolutely. So the TESS mission is a follow-on to Kepler, and the idea is to observe the whole sky. So it's an all-sky survey for transiting planets. It observes a field of view that's much, much bigger than Kepler's field of view. It's 24 degrees by 96 degrees, and so we are observing a large swath of the sky at any given time. And we repoint the spacecraft to point at a new field of view every month. And after 1 year, we've covered one hemisphere, and we flip our spacecraft upside down and then cover the other hemisphere. And the idea is to observe stars that are much closer, typically 10 times closer and 100 times brighter than the stars that Kepler observed. And we want to eventually learn what their atmospheres are made of and look for biosignatures in the atmospheres of these planets, study their climate, study their weather. And Kepler Kepler basically is putting wind in the sails of many missions and investigations to learn more about exoplanets.
Yeah, so TESS is a great follow-up to do exactly that. And as we learn much more about those planetary characteristics, here's where planetary scientists can come in and help. We can do the modeling. We've got models. We've got global circulation models of Mars and even Titan. And so there we have all kinds of tools and capability. I think it's a great opportunity for both astrophysics and planetary scientists to work together. And this helps us understand the origin and evolution of our own solar system and how we got here.
Right. It really provides the context for the Earth and the solar system and the broader tapestry of the galaxy.
I really like to ask each and every one of my guests on this program, what was their gravity assist that really got them into the field and propelled them forward to become the scientists they are today? So, Jon, what was your gravity assist?
Well, I had several gravity assists. I grew up and was fortunate to grow up in the shadow of the VAB building. Both of my parents were working at the Kennedy Space Center. The VAB building is the Vehicle Assembly Building on Kennedy Space Center on Merritt Island, Florida.
It's huge.
It's huge. In fact, when they first built it, before they got the air conditioning going, clouds would form and it would rain inside the building, my dad tells me. So my dad was an engineer at Kennedy Space Center. He worked on the Mercury, the Gemini, the Apollo program, and then on the shuttle program. And I got to watch the launches. I remember being in my PJs being brought out to watch the moon landing. And I have had a lifelong fascination with space. I think the space program and NASA's endeavors are some of the most important activities that humans can carry out. Part of it's just exploring our world and exploring the worlds around us, and part of it's just reaching out to understand where we fit in terms of how did we get here and where might we be going given everything else that's going on in the universe. So
you were really motivated based on those early exposures of what NASA was up to study hard and get a degree in astrophysics.
So I was doing my my PhD dissertation on the atmosphere of Venus. I was using data from the Pioneer Venus Orbiter and the Magellan spacecraft. And during that period of time was when I met Bill Barucki, a co-investigator on Pioneer Venus who was studying lightning in the atmosphere of Venus. And he had this really wild idea that we could find Earth-sized planets around sun-like stars. And I don't know about you, Jim, but 25 years ago, that was really pie in the sky.
Oh, it really was. So he followed his dream, and you followed him.
That's right. So he invited me to join the mission and told me, Jon, you're going to figure out how we're going to be able to find planets like the Earth, even though the stars are highly variable and have star spots. And so that indeed was one of my principal contributions to the Kepler mission.
I'm Jim Green, and this is your Gravity Assist.